So this is what we were up to. That just a quick recap that we had started talking about the strengths of acids of different organic molecules, and we had talked about alcohols being terrible acids. They hardly underwent any acid reaction. Phenols being something that's an in-between, that's slightly acidic. It can react with it can react with bases as well, but it's not going to react with carbonates or weak bases like ammonia. Carboxylic acid, on the other hand, is a pretty strong acid, relatively a strong acid. They're all weak acids, but carboxylic acid is like a complete acid, and it will undergo all acid reactions. So we talked about alcohols, and I explained, and they're going to ask you the explanation for this. Why are alcohols such bad acids? And the OH would ionize in alcohol, but it would ionize very little, and the ionization was even less than water, and water has 1 × 10⁻⁷ mole per dm cube H+ ions. So alcohols would be even worse than this. And I said that they only undergo one reaction, which is with a very reactive metal. Even in that case, it's a very slow reaction, and you only get very slight effervescence. And this was the reasoning behind that if they ask you why they're such bad acids, the alkyl chain has an electron donating effect. So what it does is that it pushes the electron density onto the oxygen. So when the H+1 breaks away, the negative charge on the oxygen is pretty large because the electrons are getting pushed by the alkyl chain. So bigger alkyl chain is going to have more electron donating effect, and the charge density increases on this oxygen, which is why it becomes unstable, which means basically that it will attract the H+1 back again. It's not going to let go of the H+1 ion. There's going to be less ionization. There's going to be stronger attraction for H+1, or you can say that the O and H bond would be much stronger because of the greater electrons over here. There's going to be greater attraction for the H+1. And this was the basic idea that if something has an electron donating effect, it's going to be a weaker acid. If a group has an electron donating effect, if a group has an electron withdrawing effect, the charge density on the ion would be lesser. It would become more stable, and there's going to be stronger acid. It's going to be a stronger acid, more ionization. So we then discussed phenols. It's got an OH. It's a stronger acid. It will react with any NaOH. It will, in both cases, form a salt. And we didn't discuss the reason for this. Why this was. I mean, we didn't discuss the reason why are alcohols better acids compared to. So I'm going to talk about that now. So why are they? So I need a benzene ring. Let me just copy one of them. So the question is, why are these phenols stronger acids compared to alcohols? So that's my phenol. It's got O and H. So when it ionizes, when this thing ionizes, what will happen is that the OH will ionize, it will dissociate. The H+1 will break away. The oxygen will get a negative charge, and the H+1 breaks away, and it ionizes in aqueous state. So it ionizes in aqueous state. It's a reversible reaction. So why are they relatively stronger acids compared to alcohols? That's the question. So in a relative sense, they are stronger acids compared to alcohols. That's your question. Why are they relatively stronger acids compared to alcohols? And the reason for that is the focus is on this negative charge. Is this negative charge strong or is it weak? What happens in phenols is that the electrons, the negative charge, it becomes delocalized. It mixes with the pi electron cloud. So the benzene ring has an electron withdrawing effect. Remember, the benzene electron density is very less. So if there's a lot of electrons over here, those electrons, they kind of mix up with the benzene electron cloud. We did the whole 246 directing effect. So the point is, the electrons will not be concentrated at this point. The electrons will get withdrawn. They'll get mixed up with the benzene electron cloud, which is why the negative charge over here is going to be smaller. It's going to be lesser. And if it's lesser, the H plus one is going to have a weaker attraction because the negative charge is lesser. So it's not going to be a strong attraction between the two. So there's more chances of the H plus one breaking away because once it breaks away, the negative charge is no longer concentrated at this point. It mixes with the benzene electron cloud and it becomes smaller, and it no longer attracts H plus one that strongly. So there's more chances of the phenol molecule ionizing compared to an alcohol. Is that clear? Bhaskar, clear? Alicia, Hafsa, Saim, is this clear?
Yes, sir.
So that's a simple reason. So if they ask you about this, this is what you're going to write, and you're going to state that the lone pairs on oxygen in the phenoxide ion. I mean, that's your phenoxide ion. You can either write the formula of the ion, which is C6H5O minus 1. So the lone pair, basically, not lone pair on lone pair on, just a second, let me correct this. So the lone pair on oxygen and the phenoxide ion overlaps with benzene's pi electron cloud. Which makes the phenoxide ion more stable. The charge density decreases. Hence the negative. So the negative charge density on the phenoxide ion, negative charge density on this thing C6H5O minus 1, it decreases and it becomes more stable. So it becomes more stable. And if it becomes more stable, there's going to be lesser attraction for H plus 1 ions. Or you can say that the OH bond becomes weaker because the O and H are no longer that strongly attracted to each other. So you can say the OH bond weakens. Hence, there's going to be stronger dissociation. Dissociation. So that is the reasoning. That's the answer to this, and they're going to be very specific about this. So you just have to explain this in either write the whole thing or, depending on the marks, just write that the negative charge overlaps, the lone pairs overlap with benzene's electron cloud. The charge density decreases, the ion becomes stable, and it no longer attracts H plus 1. So there's going to be stronger dissociation, which is why it's going to be relatively a stronger acid. Is this clear?
Yes, sir.
So relatively, it's going to be a stronger acid. The next thing is carboxylic acids too. So we talked about phenols. Remember, going back, you must identify what the OH is. Phenols are going to react with Na, NOH, but not with carbonates. Okay. I mean, I should add this. We wrote down a table earlier, but so I'm going to add no reactions with carbonates or ammonia, like normal acids. They're not going to react with them. The last one, and remember last class, I also told you that you should be able to identify which one is a phenol, which one is a normal alcohol. So if the OH is attached to a carbon chain, that's a normal alcohol. This is a normal alcohol. And if the OH is attached directly to a benzene, then that's a phenol. So we are basically talking about these phenols. So if they ask you to react, if they talk about a reaction with NOH, then it's going to be the normal alcohols are not going to react, but these OH groups, they are going to react. Now the last one is carboxylic acids. So when it comes to carboxylic acids, carboxylic acids are like complete acids. They undergo all acid reactions. This is what a carboxylic acid looks like. It's got C double bond O, and it's got OH. Again, there's an OH. So these undergo all reactions. They react with they're going to react with everything. They're going to react with reactive metals. They're going to react with bases or alkalis, and they're going to react with carbonates and also with ammonia as well. So I'm going to write reactions for each one of them. So you're able to make the equation. The salt is going to be made in the same way. So the first one is, let's have a reaction with sodium with methanoic acid, which is going to be HCOOH. So it's going to be, in this case, it's going to be the last OH that's going to get knocked out. And you will have HCOO minus 1, and Na would be, that's the salt that's going to be produced, and hydrogen gas would be given off. It's not a balanced equation. Let's make this half H2. Now it's balanced. That's your reaction. That's your simple reaction. Metal plus acid produces salt plus H2. The salt in this case would be sodium methanoate. So if the carboxylic acid is if the carboxylic acid is the sodium methanoic acid, sodium methanoate. So it's going to be sodium methanoate. Similarly, you'll have kind of a similar reaction with bases as well as carbonates. The only difference would be that in the case of bases, you'll get a water molecule that's going to be produced. So if you have NaOH, everything remains exactly the same, except that with a base or an alkali, if you have NaOH, over here, you're going to get a water molecule. That's it. Base plus acid produces salt and water. And similarly, if you have a carbonate, kind of the same reaction, it's going to be, so the same applies to this one. Let me renumber this. This is, so if you have a carbonate, it's going to be Na2CO3. N is +1, CO3 is -2, the salt, water, and you'll have carbon dioxide. And the last one is we can have a reaction with ammonia. In the case of ammonia, you're going to get an ammonium salt. So it's going to be made in the same way. It's so the fourth reaction. So if you have ammonia over here, so these are gone. I mean, and you're going to get an ammonium salt, which is NH4 plus 1. And this would be known as ammonium methanoate. So this would be known as ammonium methanoate. So remember the reactions. First one, metal plus acid produces salt plus H2. Base plus acid produces salt and water. Carbonate plus acid produces salt, water, and carbon dioxide. And ammonia plus acid ends up producing an ammonium salt. In each case, the H over here is going to get replaced. The hydrogen atom gets replaced. In the first three, it's going to be replaced by the metal, which is sodium. In this case, it's going to be replaced by the ammonium. And all of them are acid-base reactions, except for the first one. The first one is a redox reaction. Remember, a metal plus acid reaction, that's a redox reaction. It's not, I mean, this one is a redox reaction because it's not an acid-based reaction, because for an acid-based reaction, somebody has to lose an H plus 1 and somebody has to gain H plus 1 ions. Like over here, the methanoic acid molecule loses an H plus 1, and the OH ions, they gain an H plus 1, so they end up forming water. Same thing over here. This loses an H plus 1, the carbonate gains an H plus 1, the oxygen in the carbonate gains an H plus 1, and ends up forming water. Same thing over here. The ammonia gains an H plus 1, turns into ammonium ions. The carboxylic acid loses an H plus 1, turns into a methanoate ion. So these three are all acid-base reactions, except for the first one, which is, always remember, metal plus acid is a redox reaction. The H plus 1 instead gains electrons and turns into hydrogen gas. And the sodium ends up losing electrons and turns into sodium ions. So they basically, in this case, they're not losing or gaining H plus 1, they're basically losing and gaining electrons. So that's why that's a redox reaction. So these are all your acid-base reactions that you have already studied in O levels as well. I mean, are these reactions clear?
Yes, sir.
Umar, is this clear? Sam, Nadine, is this clear? Munia, is this clear?
Yes, sir. Thank you.
Okay, so we figured out the reactions, right? So I'm just going to so remember carboxylic acids. The OH in the carboxylic acid is going to undergo all acid reactions. So I'm going to draw a molecule now, like a slightly more complicated molecule. Let's say it's got a benzene ring. Let me. So here's your benzene, and let's say there's an OH group attached to it. Then there's this carbon chain that's coming out of it and going in this direction. This carbon chain has an OH group that's attached to it. And the last one has a double bond O and OH attached to it. So one by one, I'm going to summarize all the reactions that we have studied, right? So this molecule over here, what will happen to this molecule? Let me just draw a copy of this. So what will happen to this molecule if I react this molecule with sodium? Will all the OH groups react or not? With sodium?
Yes.
All of them are going to react. Okay, remember this. This is a phenol OH. This is a normal alcohol OH. This is a carboxylic acid OH. I mean, if you remember the table initially, then sodium is going to react with all of them. The alcohol will not react with all the others. It's not going to react. The phenols will react with bases. Carboxylic acid would react with everything. So they're going to react with. So in this case, the product would be each one of them, the H will get displaced, and you'll be left with O minus one, and this is going to form Na plus one. This one as well, it's going to form O minus one and Na plus one, and this one as well. All of them are going to react. So that's what's going to happen with sodium. Similarly, if it reacts with NaOH, so what will happen in that case? So let's do another one. And this time it's reacting with NaOH. Now, if it reacts with NaOH, which one of the OH will not react with NaOH?
The alcohol one.
Okay, so the alcohol, I mean, this one will, I mean, this was an OH. The carboxylic acid will react. I mean, there would be byproducts as well. We're not concerned with the byproduct. This one will not react. This OH will not react. The phenol is going to react. And the last one would be, what if I do a reaction and this time I'm going to react it with a carbonate. So if I react it with a carbonate, then only one of them is going to react. Which is which one?
The carboxylic acid.
Okay, so carbonates, only carboxylic acid would react. So you will only get a salt that is going to be produced. The H will get displaced only at this OH group. That's it. This one is for a carbonate, sodium carbonate. Here's the first thing. So you should know which of the OH. I mean, most of the questions would be very similar to this. They'll just ask you to draw the diagram. They'll give you one molecule. They'll ask you what will happen if any reacts. And they very often do this. You get a lot of this type of questions, right? So they're going to ask you, and then they'll ask you about why are carboxylic acids stronger and so on. So is this part clear, this one?
Yes, sir.
Yes, sir. Thank you.
Now, the next thing is, so we didn't discuss why carboxylic acids was stronger. So we're going to discuss that. So they're going to talk about, the next thing is, the question is, why are carboxylic acids relatively the strongest acids? What's going on there? So if they ask you, what will be your answer? Do that. We know for the reasons for alcohols being really bad acids and relatively phenols being better acids. But why are carboxylic acids? So why are carboxylic acid relatively the strongest acids? And remember, relatively, because even carboxylic acids are like really weak acids compared to your 7 strong acids. So why are carboxylic acid relatively strongest? Organic acids. I mean, if we limit our discussion to organic acids, then they are. Now, the reasoning is exactly the same. I mean, it's going to be the exact electron withdrawing donating effect. So you've got a carboxylic acid group, which is double bond O, and there's an OH. So for this to, so this is going to ionize a lot. So what happens if it ionizes? The OH breaks away. I mean, the H in the OH breaks away. So it's going to ionize, The H plus one over here is going to break away. It's going to become -1 with its electrons and left behind, and the H plus one breaks away. Why is it breaking away? Because there's a water molecule that's attracting it. So there is dissociation or ionization that's going on. So the question is, why is the dissociation greater? The reason and the explanation for that is that right next door, there's a very highly electronegative oxygen. What that oxygen does is that it has a strong electron withdrawing effect. So the end result is that the negative charge that is over here, there's a strong electron withdrawing effect. The negative charge gets pulled by the other oxygen. So the electrons kind of get distributed between the two carbon atoms. What basically happens at the end of the day is, I mean, initially you had a double bond and you had a single bond here, but all of them are going to get mixed up. The negative charge will be distributed in both oxygen atoms equally. So instead of the electrons being stuck at one oxygen or the other oxygen, the double bond electrons, etc., they all will kind of get mixed up, and the electrons will all be, so the electrons will all be, just one second, will be concentrated or spread over the entire area. So the negative charge would kind of become delocalized, and it's going to be distributed between both the oxygen atoms. So that's where your negative charge is now. I mean, this should have been, one second. So the negative charge is getting distributed between both oxygens. So your ion, your CO -1 ion, kind of looks like this. And that is why the negative charge kind of gets distributed between two atoms, and the negative charge density decreases by a much bigger margin. And the negative charge, the -1 charge, is now really small. And if it's smaller, it's not really going to attract the H plus one that strongly. So the H plus one would break away very, very easily. Is that clear? Is the idea clear?
Yes, sir.
Okay, so the main culprit is that there's an electron withdrawing effect, and that electron withdrawing effect is really strong because there's right next door, there's a highly electronegative oxygen. When H leaves, the negative charge is no longer concentrated or distributed on this oxygen atom. The negative charge gets pulled, and it kind of gets distributed on both oxygen atoms. And it relatively becomes, the charge density decreases and no longer attracts H plus one. So that's your basic reasoning behind that. So if you want to write that, it's going to be that the highly, oxygen is one of the most electronegative elements. So highly electronegative oxygen in C double bond O has a strong electron withdrawing effect. So it's got a pretty strong electron withdrawing effect. And because of that, because of the strong electron withdrawing effect, charge density on this ion, I mean, in this case, this is, I think, the ethanoate ion. We can just write RCO -1 ion, decreases and it becomes stable. What we mean by becoming stable is that it no longer is interested in attracting the H plus one back again. It wants to remain as this ion. The attraction for the H plus one now decreases by a lot. So it decreases and it becomes stable. And there's going to be less attraction for H plus one. Or what you can say is that the OH bond weakens because it's no longer interested in the H. So hence more dissociation and stronger acid. So that's.
And sir, what about the electron donating effect of the alkyl chain? Would it also become withdrawing effect too due to the oxygen?
Yeah, I didn't mention this one, but now in the next phase, we're going to discuss all of that as well. So let's assume at the moment the alkyl chain is not doing anything. Okay. Like after this, we're going to start talking about other groups now. So at the moment, I'm just talking about what's happening here. Okay. I'm not discussing the alkyl chain at the moment. Okay. Now the next thing is, but is this part clear up till this point? I mean, I'm going to start talking about the alkyl chain now after this, but is this clear up till this point?
Yes, sir.
Yes, sir.
So okay. And now the thing is, so we discussed which one is a stronger acid, which one is a weaker acid. Now what we're going to do is we're going to do within a group comparison. Like we're going to start comparing carboxylic acids with other carboxylic acids. We're going to start comparing phenols with other phenols. We're going to start comparing alcohols with, I mean, alcohols are barely any acids, so they're probably not going to give you any questions on alcohols. But we're going to do we're going to try and do some variations of carboxylic acids now. So the next thing, we have the same reasoning: electron donating, electron withdrawing effect. Like if you want to know which groups are electron donating, which ones are electron withdrawing, the reasoning behind for electron donating, you can have I'll just write electron donating groups. So you've got alkyl chains. You've got OH itself is electron donating. NH2 is electron donating because it's got a lone pair. It pushes electron density onto the other group. Who else? There's that's about it. I think that's sufficient. Electron withdrawing groups. Electron withdrawing groups can be halogens. They are electronegative, so they have an electron, kind of an electron withdrawing effect, and you can have aldehydes, ketones. Or you can have carboxylic acids, even they've got an electron withdrawing effect. Now within acids comparisons. So the first one is the first comparison is carboxylic acids with bigger and smaller alkyl chains. Okay, that's the first comparison. So now I'm going to talk about the alkyl chain. So I've got two carboxylic acids. I've got a carboxylic acid that is CH3 serial bond ON, OH. I've got another carboxylic acid which is CH3, CH2, then there's another CH2, and then there is C double bond O. And OH. So I've got these two groups. Which one do you think is a stronger acid?
Second one.
The second one is, my guess is it's probably going to be a weaker acid, but I'll explain. I'm not sure, but it's probably going to be a weaker acid. First thing, the H+ one will dissociate. So let's talk about this negative charge because it all depends on this on this negative charge. Is it strong or is it weak, right? So it depends on this thing. If the second one dissociates, ionizes, it all depends on the negative charge, like strong dissociation or weak dissociation. So you've got two carbon chains. And remember, alkyl chains have electron donating effect. Bigger alkyl chains will have even more electron donating effect, right? So bigger alkyl chains are going to have even more electron donating effect. Now, so which one in the second one? Now the C bond O group is common. I mean, so that's not a factor. Like it's doing the same thing over there. It's doing the same thing over here. So the cause of the difference between the strength of acids is not the C bond O, because it's exactly the same in both cases. So you basically look for what's different between the two groups, two carboxylic acids. So what's different is one of them has a bigger alkyl chain, so the electron donating effect is much bigger. The other one has a much smaller alkyl chain, so the electron donating effect is a lot smaller. So who's going to have a bigger negative charge, this one or this one?
Second one.
So the second one is going to have, it's going to have a larger negative charge. The charge density over here would be much higher. And the first one will have a much smaller negative charge. So the second one is less likely to dissociate because there's going to be a stronger attraction for H+1. The OH bond is going to be a lot stronger, so it's much harder to break it. The H+1 would be a lot strongly attracted to the O over here. Is this clear?
Yes, sir.
Bakyo, is this clear to everyone? Nadine, Sam, Saim, Munya, is this clear?
Yes, sir.
Yeah, thank you. It is.
Okay, so they're going to do a lot of comparisons. So you have to. So we did which acids were strong, which were, I mean, we did the whole carboxylic acid thing, and now it's a within carboxylic acid comparison. So, and they'll ask you for the reason for that. So, the simple reason would be, I mean, the reason for that would be bigger alkyl chains. So more electron donating effect. So, I mean, this one is the stronger acid. We should write that. So more electron donating effect, which would make, this one is the weaker acid, sorry. It's not going to dissociate. It's not going to ionize. So bigger alkyl chains, more electron donating effect, and so this ion, this big ion, CH3, CH2, CH2, CO -1 ion becomes unstable. So everything, the rest of the reasoning is the same. It becomes unstable and has lesser. So he has higher charge density. So it's got a higher negative charge density, more attraction for H+1 ions. Or you can say that the OH bond becomes stronger. So that's the reasoning. Now the other one that they're going to talk about is carboxylic acids with chlorine substituted carboxylic acids. So if you have chlorine substituted carboxylic acids, then what will happen is that so depending on, now this one we can discuss that in the next class. Then it's going to take some time because there are different ways that chlorine is going to get substituted. So So we're going to talk about this. Remember, chlorine has an electron withdrawing effect. So it's going to be the exact opposite of this. Like if you've got a Cl, then the electrons are going to get withdrawn because of the highly electronegative Cl atom. So we'll talk about that in the next class. Is this clear, this thing so far?
Yes, sir.
Yes, thank you.
Okay, and so let's continue next time. Munya, I'm going to discuss your question now. So this class is over. I mean, you can leave the class if you want to. I'll just discuss the question.